All right. So sorry about yesterday. We'll tackle this asynchronously and definitely come to me with any questions that you have. I want to remind you that we're skipping 24.4 now, and we'll come back to Gauss's law when we introduce magnetism. I wanted to keep you on track with lab. Okay. Previously, what have we talked about? We've talked about electric fields. Whoops, there we go. And we've defined electric fields as this equilibrium constant. Too many classes with too many K's. Where they're Coulomb's constant, or electrostatic constant, there we go, times the charge creating the field divided by the distance away from that charge that we're measuring it. And we've done things in all sorts of different directions and different configuration of charges. But for now, we're going to start thinking in terms of like an overall cue for things. And we'll talk about geometry here in a bit, but not today. Let's see, what else have we talked about? We said force, then, is some charge interacting with an electric field. And we decided that, we didn't decide, I told you that, for a negative charge, let's make this negative and just draw a circle around it, that fields go into a negative charge. That's how we're defining it. And for a positive charge, fields go out of. And then the other thing that I have been repeating to several of you is be very careful with the language that you're using. Don't describe fields as forces, and not to use the term energy with things. And today you're going to find out why I keep repeating that. Today we're going to introduce this thing called electric potential and electric potential energy. Two different things. And all of this energy. I'm going to run out of room, so I'll stop there. There we go. I'm going to start by talking about electric potential in terms of a gravitational field, and then we're going to kind of pull things apart so you can see the difference between potential and potential energy. So let's kind of back things up to first quarter, where we talked about gravitational potential energy and gravitational potential. No, we never talked about gravitational potential. We just talked about potential energy. And we did it in terms of the distance away from the center of the Earth, and we described this thing called g, the acceleration due to gravity. And we said, quite honestly, if you're close enough to the surface of the Earth, that g's not changing by much. It is only when you got far away. That's going to be different for our electric potential, because we're dealing with much smaller things causing that force acting at a distance, whereas gravitational potential is related to this ginormous earthy thingy that we're standing on. And so that distance away, if I move a few meters up, isn't really that much different compared to the whole radius of the Earth. And anyhow, so we'd say something like, I stand up here at this point 2, and in terms of what's happening to me, let me draw me in there, with that position 2, if I jumped off of that and went down to this position 1, what we said is that I had gravitational potential here, gravitational potential energy here, and that by the time I hit the ground, that was all converted to kinetic energy. So we did a lot of roller coasters, which is fun. You start off at the top and you're going really slow and you're getting ready to go down a hill. And so you have just a little bit of kinetic energy, and then you go down the hill and and then you get down to the bottom, and most of that potential has been converted into kinetic, minus some that's lost to air resistance or friction. But what we've explained this quarter is it's not just this thing, this force due to gravity. It's actually a field that you're interacting with. And then we kind of segued that into this electric field. But when we talked in terms of energy, remember this here, this mg delta x. Let's see, what was that saying? That was saying that I have, let's see, a mass and an acceleration. So this thing is a force. over some distance. And we defined those units then to be joules. So force times a distance, that could be the work done on you by gravity, the force of gravity, would give you this energy, right? And so if I move against a gravitational field, I am gaining gravitational potential energy. If I move with a gravitational field, I am losing gravitational potential energy. Let's now think in terms of a charge in an electric field. And I want to remind you, we said that electric fields are defined as the field lines going into a negative and out of a positive. So if I bring a charge up here, say a positive Q, and let it go, well, what am I? I'm in like this positive area, so I'm up on a high dive, and I'm going to jump into the water. I want to go, in the case of a charge, where it's attracted to. In case of potential energy, it's just where gravity takes you, right? So this is the charge interacting with the electric field. So I would start here at high potential, and I'd end here at low potential. So a positive charge moving in the direction of an electric field is losing potential energy. And if I move against an electric field, positive charge, I'm gaining potential energy. Now, if I do the same thing, if I take a negative charge, well, let's see. It's at its happy place here, right? It's with positive charges, and I'm going to make it move in the direction of an electric field, meaning I'm making it move towards something it's repulsed by. In this case, moving against the field, I'm sorry, that's moving with the field lines. So moving with the field lines, this would be gaining. Moving against the field lines, well, that would be me moving this way with a negative charge. So this would be losing potential energy. This potential, this thing here, is the new thing for us. I'm going to rewrite what I wrote up top, that we defined a force related to electrostatic charges is some charge interacting with a field. And remember, we said energy is a force at a distance. So energy in terms of electrostatics would be this Q interacting with the field, that's my force, acting at some distance. Now I have energy. But this delta V here, what's going to happen if I go energy divided by Q, and actually I should write them in the same so they don't look different. If I go energy divided by Q, what do I have? I have Q E delta X divided by Q. My Q's cancel. So this thing we are calling potential is just my electric field at some distance. It's measuring from some given point, some arbitrary point we want to measure between 2 points. We're going to measure the change in the electric field between those 2 points. And we're defining that as our potential. The way I like to think about that is, here's my horrible drawing. That's a high dive. And here's some water. I'm going to draw in another one. And here's some water. They both have the same height. My delta X is going to be the same for both. It's the same. How do I convert this ability of this high dive to do something exciting into energy? Well, I got to add something in. I got to put somebody on the high dive. Once I have this person here, now that I can say that they have potential energy related to gravity, and if they dive, right, then all that potential is converted to kinetic. Well, I still have the high dive. It's the tree falling in the forest and nobody hears it. This delta X still exists on this high dive, but nobody is there to experience it. So this is just potential. This would be like potential related to gravity. The cliff is there. Nobody's in Acapulco to take advantage of said cliff and to dive into said gorgeous water. But the cliff is still there. So the potential still exists. I convert it into potential energy by having something experience it. So with my energy related to an electric field, as soon as I introduce a charge to interact with that field, now I have energy. Now I've capitalized on the fact that that field exists, because it does. So long as I have a source creating a field, the field exists. Potential is that that field exists. Potential energy then comes from something, a charge, interacting with that field for some given distance. So we're taking the force and then looking at a distance. Oops, I didn't erase everything. It's my second time through doing this because I had to kind of stop. This thing here, this is a parallel plate capacitor. We're going to talk about that more detail on Monday. But this parallel plate capacitor, you'll notice that the lines, the field lines between the two plates is exactly the same. If the field lines between the two plates is exactly the same, so they're all pointing in this same straight direction, then that means the electric field is constant. And what you'll see in your textbook is it'll say two infinite parallel plates, that the electric field is constant between those plates. What they're not mentioning is that in real life we get this distortion. That's what I had drawn in here. We get this distortion between. Now let's think about how we can relate potential to our electric fields. Well, here's the fun thing. The way you would do that is I would take a probe and I'd put it here and like here. And I'd measure the distance. Now remember, when we talked about our probe, we said that is a charge much, 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 much smaller than the thing creating the field. Therefore, it doesn't disturb the field. So when I measure these potential, I take a voltmeter, I'm measuring just potential, a change in potential between two spots. And what I would find is, like, if this was like something like 10 volts, that my charge, when it's closer to here, is going to be closer to the 10 volts, and then by the time it gets to here, it would be like at 0 volts. And we should really take the charge out there, because I'm not talking about an actual charge interacting, I'm looking at my probe. And so what I would see is just this linear change, because my field lines are always going to be perpendicular to my potential lines. And if you measure those carefully out in lab, you would get like these very evenly spaced potential differences. You have this linear change between point to point. I'd be like -5, -1, -2, -3, -4, all the way to 10, right? So I'd lose 1 each time for each little space that I'd measure until I get to 0. And those spaces between those differences are going to be evenly spaced. So I have this very linear change. So the takeout here is that potential, can I spell? Yes, I can spell. Yay me. Is going to equal what then? It's going to equal my E field, and that delta X is the little spaces in between that I'd be measuring. So let's see that a consistent change between those electric field lines. In fact, what we do is have you do the probes and then connect the dots. It's all you do in lab. You connect the dots between the lines. So anything with the same potential would get a line drawn through it. Then you take your electric fields and you draw them perpendicular to the potential lines. And when you do that is when you see something like this. So for a point charge, we're going to have the same thing, this E, but you'll see this other notation of delta R. And why do you see that instead of a delta X? Well, because we've defined everything as E equals KQ over R squared. So my E times delta R. B equals E times delta R. Let's rewrite that. KQ over R squared times R. So my potential, if I don't have a field to just grab onto, a field that's already been determined, I'd have just my electrostatic constant times my charge divided by R. That's my potential. This thing here is scalar. Whew! No more vectors for a while. You get a little bit of a break. So my potential is a scalar quantity. And this is why I really don't like doing this lecture before you take the exam, where I keep reminding you not to use your signs for your charges. We're going to do the exact same in the next video, where I'm going to show you that we can add up all of my different potentials if I have more than one source. And when we add them up, now we're going to take into account their signs. So now you can take the sign of the charge and incorporate it, because we're dealing with the scalar quantity. We're not dealing with the vector quantity anymore. The only other thing I want to emphasize here is that these would be for constant. Constant. Okay. So with that, I am going to stop and then come back and do the next page on this handout.